Hello everyone, and welcome to this video titled Derivatives and the Shape of a Graph, Part 1, the First Derivative Test. So in this video, I'm going to be taking you through part of a preview version of a Knewton Alta homework assignment that is also titled Derivatives and the Shape of a Graph. I'll be specifically going through the heading for the derivative objectives that is called the First Derivative Test. Please understand that this is a preview of the assignment, so the questions that I work on in this video may not be the same as the questions that you work on while you're working on the assignment yourself. But the objectives are the same, and the methods I use to get through particular questions should be similar to what you're doing. Okay, so here we are at Knewton Alta, and this is a preview of the derivatives and the shape of a graph assignment, which for the particular course I'm teaching is section 4.5. In the upper right hand corner, you'll have a mastery bar that tells you how far along in the assignment you have gotten. Next to that, an activity log. So you see this, this tells you how many objectives are in the assignment. And this one's a pretty long one. So I've decided to break it up into 3 parts based on the heading titles, because there are 9 objectives with 3 broken up into 3 parts, 3 headings. So in this video, I'm going to be going over the 4 objectives under the heading, the first derivative test. All right. And then part 2 will be on concavity and points of inflection. And part 3 will be on the second derivative test. Then on your home page, you have your current objective, then a question beneath that, related to that objective. And at the bottom of every question, you should be seeing a feedback option, feedback button. So if you notice any errors in the question or in the answer explanations after a question, you can send feedback directly to Knewton support, and hopefully someone gets back to you relatively quickly with a way to help you fix your issues. I hope it's obvious that you will not have the instructor cheat button. It's for instructors only, demonstration purposes only. But you will see a more instruction button. So if you're working on an objective and you don't recall the material too well, or you'd like to study it further, you can click on more instruction, open up the instruction, and you'll be given reading to do or videos to watch, or both, related to that particular objective, and hopefully that will help you, get through the assignment. And then some questions like the one I'm seeing here have this show steps option, where you can be taken to a similar question that's, not like this. It's very much like this one, but it's broken down into steps to help you practice. So you can do that if you wish. Okay, so before I get into the questions, I will discuss this first derivative test and what the first derivative tells us about the shape of a graph. So this will be all specifically about what the first derivative of a function tells us about the graph of that function. Now, of course, when I say we're given a function, say f of x, y equals f of x, I'm assuming that we have a differentiable function, right? The first derivative exists over its domain, so because it would be silly to talk about the first derivative if the first derivative, didn't exist. So given a differentiable function, say f of x, if you look at the first derivative, so where f prime, so again, you take a look at the first derivative, wherever f prime is positive, okay, greater than 0, the graph of f will be increasing, will be going up. The outputs will be increasing, going up as you go from left to right. And I'll draw a little picture of what I mean here. So wherever the first derivative is positive, the graph of the original function, right, so the graph of just f will be increasing. You could say going up as you go from left to right. Right, and think about it. If you're looking at the graph of, say, here's the graph of some function, there's the graph of f that's, it's increasing. As I go from left to right here, it's going up and up and up. So remember what the first derivative means. The first derivative tells you at any particular point. So if I were to take a point on this curve that's going up like this, remember the tangent lines have positive slopes on pieces of the graph that go up like this, that increase. So in other words, f prime is positive. Means the same thing. Because remember, f prime, the first derivative, told you the slope of the tangent line to the curve at a particular point. So on pieces of curve, pieces of the function that are going up like this, positive first derivatives. And then, of course, the other way around, where f prime, right, again, where the value of the first derivative is less than 0 is negative. The graph of the original function will be decreasing. The outputs will be going down. The y coordinates will be decreasing. So the graph of the original f of x will be decreasing. Or you could think of it as, going down as you move from left to right. So a similar picture, right? If you look, here's the graph, here's a piece of curve, and say the graph of f, right? Not f prime, the graph of f, the original. And as I go from left to right here, right, it's going down and down and down, a decreasing piece of function. So remember, if you were to take any point on this curve, this piece of function here, and look at the tangent line, right, the tangent line would have a negative slope. And that'll be the case for any point on a piece of curve that's, going down as you go from left to right. So again, tangent, so a way to say this again would be tangent lines on pieces of curve like this have negative slopes, which means the same thing as we stated up here. That means the first derivative at these points, right, f prime, is less than 0, right, it's negative. All right, and then, so this is where derivative is positive, where the derivative is negative. Then you have two other options too, right? There's always four possibilities when you're evaluating things in the real numbers. You're positive, you're negative, you're zero, or you're undefined. So when f prime is 0, so this means the slope of the tangent line is 0. Right? You have horizontal tangent line. The graph, I'll just write that out here. The graph of the original function of f has a horizontal tangent line. Now, we'll bring up the first derivative test that this video is going to be about, that this particular heading in the assignment is about, after all this discussion here. As a horizontal tangent line, so it kind of flattens out, right? Horizontal being nice and flat, horizontal left, right. So you got pretty much a few ways this could happen. So I could have a graph where you're increasing, and then at a point it flattens out, and then it keeps increasing. But again, at that one point there where it goes, increasing, flattens out, increasing again, and I'll write that here. We could call this flattening out, flattens out. So that could happen. Or it could be, maybe decreasing and flatten out and then keep decreasing. So again, at a point like this where it's flat horizontal tangent line. But then there's the points that we're going to be focusing on later with this first derivative test. So you could also have this happen where it increases, flattens out, and then decreases. So again, nice flattening out, top of a hill type situation. So remember, at a point like this, they would say the function f has a local maximum value at a point like this. I'll just say a local maximum. And that's what the first derivative test is going to help us determine, is if we have one of these local extremes, a local maximum value, or you could have a function that's decreasing, then flattens out, and then starts increasing again, right? Decreasing, then increasing. So at the bottom of a valley here, again, where it flattens out, has a horizontal tangent line. And you may recall from a pre-calculus course talking about tops of hills, bottoms of valleys like this. At a point like this, they would say that the function f has a local minimum value. All right. So again, the first derivative test will be about finding these places, finding these points where the function has a local extreme, right? A local max or a local min. But notice that just because the derivative is 0 right, doesn't mean you're at the top of a hill or bottom of a valley, right? You saw these first two pictures here where you could be increasing, then continue to increase, or decrease, flatten out, and then continue to decrease, right? So just because the derivative is zero somewhere doesn't mean you're at one of these local extremes or extrema. So we'll focus on these, right? You say but if you're going to have a local extreme, the derivative is either going to be zero or undefined, as we'll see on the next page. So when the derivative, so again, first derivative f prime, is undefined, or DNE, right, does not exist, undefined at a particular point, well then the function is either, just not continuous there or not defined there. So I'm not going to draw those, right? Because obviously if the function isn't, if the original function isn't defined there, then the derivative won't be, right? And you're not going to be continuous there. So I'm not going to draw those pictures. But if f prime is undefined, then the graph of the original function, again, either might be just discontinuous there, but the graph of f, so say the function is defined at this x value, will either have a vertical tangent line or a sharp point, a sudden change in direction. Will either have a vertical tangent line, so straightening up, it's flat but vertical at the point, or a, sharp point, a sudden change in direction, right? So here's what I mean by that, where, the ones with the vertical tangent lines, you could have a graph that's increasing and then at a point, kind of straightens out vertically and then maybe continues to increase, right? So like in your cube root function at zero, vertical, I got a vertical tangent line at this point. At that moment, you're looking straight up and down. And something similar to that would be if I was decreasing and then flattened out, straightened up a bit here, and then continued to decrease. So again, at a point like this, still looking straight up and down at this moment, vertical tangent line. So the derivative, the first derivative would be, undefined, right? This is a vertical line had an undefined slope. But those aren't the only points where you have no derivative. You could have like your absolute values where I'm increasing, hit a point, and then have a sudden change in direction where I'm decreasing. So this is what I meant by the sharp point. Right? This is, not smooth. They would say the function's not smooth at a point like this where there's a sudden change in direction. Still, at these points where the derivative doesn't exist, and this will be the first derivative test. You find these places where the derivative doesn't exist or where the derivative is zero, as we saw on the previous page, and then you look to the left and look to the right and see if it's increasing and then decreasing like this. If it's increasing on the left and decreasing on the right of this point, then you'd have a local maximum, right? F has a local maximum value at this point. And you could have another one with a sharp point. Or maybe again, this is one here where maybe it has a vertical tangent line, but still a sudden change in direction. In one of these sharp points, these cusps, places where the function is not smooth. But still, if you look to the left, it's decreasing, and you look to the right, it's increasing. Well, then you're at the bottom of a dip, bottom of a valley here. So in that kind of a place, the function has a local minimum. Now be careful though, right? Just because the derivative doesn't exist, right? You saw in these pictures here, doesn't mean you have a local extreme, right? Doesn't mean you have a local max or a local min. And even at the sharp points, I could have a function that was doing this, and then at some point it just does a sudden turn and keeps going up. Like this point here, right? The function is not smooth. It's a sharp point, a sudden turn at this point here, and it's increasing from the left and then increasing to the right. So this is neither local max or local min, right? Same thing with these 2 points here. Right? These are neither a local maximum or local minimum value of the function. But still, all this discussion here leads me to this first derivative test. All right. So the first derivative test, this is a way to determine where the local maximum values and local minimum values or local extrema of the function are, right? To determine local, right, these hills and valleys, extreme values of the function. Let's say we'll call the function here f of x. So first, we find the values where the first derivative equals 0 or where the first derivative is undefined. Because you saw in my previous couple pages, when the first derivative is 0 and when the first derivative is undefined, you may have these local extreme values, right? Tops of hills, bottoms of valleys, but these are the only two cases where that could possibly happen. So you find these values. Now these are referred to quite often as the critical values of the function. These values where the derivative is 0 or where the derivative is undefined, they may be referred to as critical values. Then, for critical values that are actually in the domain of f, right? Because if you find these and they're not in the domain of the original function, there's no point in talking about them. You're not going to have points on the graph then at those values. So for critical values, in the domain of f, they got to be in the domain of the original function for us to even worry about talking about them. So for the critical values that are actually in the domain of f, we're going to look at the values immediately to the left and immediately to the right, look at the values around that critical value and check the value of the first derivative, right? That's why this is called the first derivative test. So if f prime is, positive to the left and f prime is negative to the right of the critical value, then the function will have, if it's positive to the left, that means the graph is, increasing, or positive first derivative and increasing. And then we have the place where the derivative is 0 or undefined. We have our critical value point. And then negative to the right, the first derivative is negative to the right, so it's decreasing. So you see at those points, the function will have a local maximum value at that critical value. So f has a local maximum at that critical value. The other way around, switch this up. If the first derivative is negative, all right, so sorry, less than 0, less than 0. So if it's negative to the left of the critical value, all right, on the left side, that's to the left, and also f prime is positive, to the right or on the right side of the critical value. So that would be this case where, decreasing to the left, then you have your critical point where the derivative is 0 or undefined, and then increasing on the right, positive first derivative on the right. So you see at those points, you'd have the graph of the function has a local minimum value, right, bottom of a valley. Then f has a local minimum value at that critical value, at that critical point. Okay. Now, if neither of these things are happening, then you're not going to be able to say that you have a local max or min. So I had pictures up earlier, right? If it's increasing on the left and increasing on the right, not happening. If it's decreasing on the left and then decreasing again on the right, that's also not, there's no local extreme there either. So it's pretty much at any point where the value of the derivative changes sign, right? Goes from positive to negative or from negative to positive. That's where you're going to have these local max and local mins, local extreme. Right. So now we can finally get into the questions from the assignment. So we're given a function. And so this first one is, use the first derivative test to find these local extrema of an algebraic function. Right? So you got a function involving rational powers, roots and powers and, you know, adding, subtracting, multiplying, dividing with the input variable. So use the first derivative test to find the location of all local extrema for the function given below. Enter an exact answer, right? No rounding. And if there's more than one local maximum or local minimum, write each value of x separated by a comma. If a local maximum or local minimum does not occur on the function, enter the empty set symbol in the appropriate box. All right, so we have this function. All right, I'll write it out. So f of x equals, this is negative 7 times x to the 5/3 power plus 2 times, now they have the cube root of x, but I'm going to write this as x to the 1/3 power. That's the cube root of x as well. Now before I do anything, I like to state the domain of our function, so I know what's allowed to be plugged in, where we're going to have points on our graph. Now this is cube root. Notice the denominators on these powers are odd, and there's no negative powers, so I can plug in 0. Right? 0 to a negative power is, undefined. But there's no negative powers, odd roots, right? So this is all real numbers. The domain here, I can plug in any value for x I wish and get a real number output. And I'll go to Desmos in a little bit. We'll take a look at the graph of this and see that it's got a point for every x. No matter what you plug in for x, there's some point on this graph. All right, so now we're asked to find the local extrema, right? The local maximum values of this function, local minimum values of this function, using the first derivative test, right? So I find the first derivative. So here it's just a simple power rule, go term by term, applying the power rule here. So first term here would be negative 35/3 times x to the 5/3 minus 1 would be 2/3, right? 5/3 minus 3/3, and then plus 2/3 times x to the negative 1/3, or sorry, negative 2/3, right? 1/3 minus 3/3, so x to the negative 2/3. Now I'm going to do a little factoring here to make finding the critical values a little easier. So you notice how both of these have, I'm going to pull out, because the lead has a negative, I'm going to pull out a negative 1/3, right? Both of these have a third in common. And the lowest power of x is x to the negative 2/3. And if I factored that out, we'd have positive 35 times x to the 4/3, positive 4/3, right? If you were to redistribute this, you'd get this first term back. Then just plus 2, right? Or sorry, minus 2, because I pulled out a negative. So 35x to the 4/3, minus 2. And now hopefully you see that this derivative is undefined at 0, right? When x, remember, 0 to a negative power, that's 1 over 0, that's undefined. So here I'm going to talk about the critical values. All right, let's go about finding those. So again, the first derivative here is undefined at x equals 0. And notice that that is in the domain of my function. All right, so I'm going to talk about whether or not we have a local max or local min there. And then the first derivative equals 0 when this other factor is 0, because again, this first one would be 1 over, negative 1 over 3x to the positive 2/3. That'll never be 0. The numerator is never 0. But this factor will be 0. Right, this equals 0 when x to the 4/3 equals positive 2/35. I would add 2, divide by 35, and so we'd have, actually, there's 2 possibilities here. Well, there's actually quite a few. remember when I raise both sides to the 3/4 power, this is taking an even root of an even power. So I would technically have the absolute value of x over here instead of just x, and equals this 2/35 to the 3/4 power. So I get two possibilities, right? Two values of x that give me a derivative of 0 horizontal tangent line. One is positive, 2/35 to the 3/4 power, and the other one is the opposite of that, right? The opposite of 2/35 to the 3/4 power. All right, so again, those are not nice values, but these are the values where my first derivative is equal to 0. All right, and every single one of these, 0, this positive 2/35 to the 3/4, this negative, 2/35, the opposite of 2/35 to the 3/4, all these are real, so they're in my domain. So what I like to do, what we're going to try to determine is where the local maxima occur. So I make a little number line for the derivative. Make a number line for f prime. So here's a number line, possible values of x. And then this is a number line for f prime. So on the line, I mark off these critical values that are, actually part of the domain up here. So again, at 0, the value of the derivative is undefined. So I just put a little UND above this, right, and tell me that at x equals 0, f prime, is undefined. And then we have this, positive 2/35 to the 3/4 power, whatever that value is. So at this value, the derivative is, 0. And then we have, the opposite of that. So over here, negative, and then 2/35 to the 3/4 power. The value of the derivative is 0. All right, so I'm actually going to go to a calculator and see what these values are approximately. So going to Desmos here. So I'm going to put in our derivative expression. So I'm going to call this g of x, right? I know it was f prime, but I don't want to call it f, right? It's not the same as f. So here was our derivative expression. It was negative 35 thirds. Oops. 35 thirds times x to the 2/3 power, then plus 2/3 times x to the negative 2/3 power. Okay, so this was our derivative function. And remember I said so I want to see what this value is, this 2/35 to the 3/4 power. So yeah, this is a little bit bigger than 0.1. And maybe you can see from the graph of the function here that between these two values, got positive derivatives, right? The output's positive. And then outside these two values, the derivative's negative. I got negative output. So that's what I'm going to mark off on my number line here. So you see between the two values, the value of the f prime, the value of the derivative function that we saw was positive. So I put little plus signs here. And then outside these, right, we saw in the graph of the derivative there that the outputs were negative, right? So negative derivative for values outside these. Now remember what this says about the original function. So wherever the derivative is negative, that means the value of the original f, right? So this is f, not f prime, is decreasing. So I'll put a little down arrow. So from negative infinity up to this, opposite of 2/35 to the 3/4 power, the graph of our original function will be decreasing. And then between this opposite of 2/35 to the 3/4 power and 0, got positive derivatives, so the graph of our original function, f, will be going up. I'll put a little up arrow. F is increasing. And same thing over here, between 0 and 2/35 to the 3/4, got positive derivatives, so f is increasing again. And then from 2/35 to the 3/4 power onward, the graph of our original function will be going down, will be decreasing because there are negative derivatives. So by this first derivative test, you see how at this value here, this opposite of 2/35 to the 3/4 power, to the left you're decreasing, to the right you're increasing. So the original function, and I'll show you this in Desmos in a picture of it, the graph of our function f up here will have a local minimum at this x value. As you're going down and then up here, you'd be at the bottom of a valley here. And then at the positive 2/35 to the, the positive 2/35 to 3/4 power, see how to the left increasing, to the right decreasing, so you're at the top of a hill. So f has a local maximum value at this x value. Right, and we'll see that in the graph. And then at 0, now again, 0 is in the domain of my original function, so I should check it. Now you see how to the left increasing, to the right still increasing. Positive derivatives on both sides. So this is neither. So at 0, you're going to see one of those where it's increasing. Maybe that's probably, it's doing this. It's got undefined slope. And then that is doing something like this at 0, where it's not at the top of a hill or bottom of a valley. So my answers are going to be local min at x equals, this opposite of 2/35 to the 3/4 power. And the local f will have a local max at this, 2/35 to the 3/4 power. Those are what, they said enter an exact value, so those are what I'll be entering. Now again, let me go back and show you. Here was our original function, right? This f, right? That was the derivative I had up earlier. So f was given as negative 7x to the 5/3, then plus 2 times x to the 1/3, right? The cube root of x. And look, you see this here, and this here, and this here, right? So see at 0, got a vertical tangent line, right? Not at the top of a hill or valley. But then remember 0.116, right? This was that 2/35 to the 3/4 power x value. So you're at the top of a hill there. You're got a local maximum value of this 0.78. And then you have a local minimum value of negative 0.78 at that opposite of 2/35 to the 3/4 power, the negative 0.11687. So you're seeing that in the picture. So just those two. So back on the problem here again, local maxima occur. There was only one of them, and it occurred at that 2/35 to the 3/4 power. And then the local minimum value you saw occurred at the negative, the opposite of that 2/35. Be sure that that negative sign is not in the parentheses here, because if you do put it inside, right, it'll be imaginary. So it's opposite of outside, 2/35 to the 3/4. And that should do it. All right, and then when you submit an answer, it's going to tell you if you're correct or incorrect, and then give you some sort of answer explanation. Now, they wrote it with the fourth roots and all that. Yuck. Still, whatever you enter, as long as what you enter is equivalent to what they have, they should give it to you. So, yeah, you'll be given some sort of answer explanation. I'd highly recommend reading through these, whether you got it right or wrong. If you got it correct, maybe you did the problem in a very inefficient way, and you read through the answer explanations, and they do things in a way that you like better. So you might want to try that for a future question that's very similar. Obviously, if you got it wrong, read through the answer explanations, try to figure out where you went wrong, why you were wrong, and hopefully you can learn from your mistakes for future questions that are like that. Okay. All right, so now we're, once again, another objective here in the same area, the first derivative test. So use the first derivative test to find local extrema of a function given its graph. So this is one of those interactive ones, right? I gotta move some points around, move some stuff. So consider the graph of f prime shown below in blue, right? So this is the graph of the derivative, kind of like in the last one where I, looked at the graph of the derivative first and then the original. Submit your answer to this question by completing the following tasks. All right, so the question is, how many local minima does f, right, the original function, have? Slide the black point on the upper left corner of the graph to select the number of local minima of f. So if you look at f prime, this is again the graph of f prime. Remember, where the derivative is 0, those are your critical values. So there are 1, 2, 3 places where the graph of f prime crosses the x-axis. There are 3 critical values here. So this one on the left, where my cursor is floating around right now, see how the value of f prime is positive to the left of it, and then below the x-axis, negative to the right? So you'd have a local maximum at -4, local max. And then here at -1, looks like -1 where the f prime is 0. See how to the left it's negative, to the right it's positive. So you have a decreasing f and then increasing. So here at -1, the graph of the original, the graph of f, would have a local minimum. And then here at 1, looks like 1. Got positive derivative, positive outputs to the left, negative derivative to the right. So increasing f, then decreasing f. So you'd be at the top of a hill, a local max there. So the only place where you go from negative derivative to positive derivative, where you'd have a local min, is here at -1. There's only one local minima, right? So I'm moving this black thing, this black point over to where it says 1. So 1 local minima on f. So it says slide the black point upper left corner to select the number of local minima of f. So there's just going to be the 1. And then for any local minima that exists, identify the x-coordinate of each local minimum of f by dragging the corresponding movable point to the correct spot of the graph of f. So they got the 1 point here. Move it to the critical point, right? See at -1, that's where the derivative is 0. F prime is 0. And to the left, f prime is negative. To the right, f prime is positive. So again, the graph of the original f would have a local minimum value. It'd be at the bottom of a valley here at x equals -1. And that's it. So once you've got the right points placed, hit submit. Great. so switching the objective again. So understand the relationship between the graph of a function and the sign of its first derivative. So this is where I mentioned earlier how, right, when the first derivative is positive, function will be increasing, will be going up as you go from left to right. And where the derivative is negative, that's where the function will be decreasing or going down as you go from left to right. So consider a function f. So they tell us the function has critical points at -2/5, -1/5, 0, and 1/4. The table below shows the open intervals between each of these critical points and the sign of f prime, right? The sign of the derivative, whether the derivative is positive or negative on each interval. On which intervals is the function increasing? So remember, the function f is increasing where the derivative is positive. So that would be on this interval from -2/5 to -1/5. Got a positive plus sign there, right? From 0 to 1/4, and from 1/4 onward. So those three, -2/5 to -1/5, 0 to 1/4, 1/4 to infinity. Very simple one. Just selecting the ones with a positive derivative. Now, if they asked for where is f decreasing, then it would be the ones with the negative derivative. And that's it. Very quick and easy one there. All right, so back to this one where we're given a function and asked to locate where would the function have, the top of a hill, bottom of a valley, local maximum values, local minimum values. But it's just a different, different kind of function, a rational function here. All right, so let's write this out. So the function we're given this time. So we have a rational function, right? I'll just put the negative in the numerator. -6x divided by, and then 6x squared plus 8. Which actually, I'm going to simplify this a little bit. You can factor a 2 out from these, and 2 goes into 6 3 times. So this will simplify to -3x in the numerator. And if I factor the 2 out down here, it would be 3x squared plus 4. Okay, just to look at smaller numbers. Now, once again, because I only want to work with critical values that are actually in the domain, state the domain of this function. So the domain of this function, the domain of f, let's do an interval notation. Now it does have a denominator, 3x squared plus 4. That'll never be 0 for any real value of x, right? Because if not, this was 3x squared minus 4, then you'd have some values where the denominator would be 0. But this is once again all real numbers. Any value of x will give me some real number output here. All right, so whatever critical values I find, I'm going to have to look at all of them to determine if we have any local max or min on the graph of f. All right, so I'll go through, find the first derivative. Now I'm working with this one, the simplified version. Remember this, I'm doing the quotient rule here. So remember how the quotient rule goes. You got your denominator multiplied by the derivative of the numerator minus, the numerator multiplied by the derivative of the denominator, which should just be 6x. And then all that, divided by the denominator squared. And then I'll actually simplify the numerator, distribute the -3 to this factor, and this here just be positive 18x squared plus 18x squared. All right, so putting some stuff together, you have -9x squared, but then plus 18x squared would be positive 9x squared for the x squared terms put together up there. and then minus 12. And then down here, 3x squared plus 4 squared. Okay, well, the denominator will never be 0. Right, just like 3x squared plus 4 earlier, right? You take any real number for x, this denominator is always going to be some positive value. So the denominator is never 0. So this is never undefined, right? So when I go to state my critical values, when I say, hey, where is f non-existent, I'll just put dne here. That does not happen for this one. So now we got to focus on where the derivative is equal to 0. And if you look at the numerator, you could factor that pretty nicely. Pull a 3 out, then you'd have 3x squared, minus 4. And this will be equal to 0 when x equals, you know, positive or negative square root of 4/3. So this happens at x equals, positive square root of 4/3. I would add 4 divided by theta square root. Right? Or x equals the opposite of the square root of 4/3, which I'm just going to write like this. Now you could simplify this, make this 2 root 3 over 3 if you want. If you totally rationalize the denominator, same thing with this would be negative, 2 root 3 over 3 if you rationalize things. But I think it takes less typing to do square root of 4/3, negative square root of 4/3. All right, so like before, here's a number line, possible values of x, and it's a number line for, the first derivative. And we only have these two values that are important, these two critical values, negative square root of 4/3, where the derivative is 0. So f prime is 0 at this value, and positive square root of 4/3, where once again the derivative is 0 at this value. And then I'm plugging in values around these to see if the derivative is positive or negative. So again, we're going into the derivative. Now, I already told you the denominator, this denominator is always positive. Right? It doesn't matter what I plug in. So really what matters is the numerator. Now, between these, I could plug in 0, and you can very easily see that the numerator will be negative for the derivative expression, right? The numerator will be negative, the denominator will be positive. So I have negative derivatives, with little minus signs in here, between these two values, negative first derivative. And then, 4/3 is definitely less than 4. So the square root of 4/3 is less than 2. So if I plugged in, say, 2, that would be beyond this. And, you'd have 36 minus 12 at the positive numerator, positive denominator. So you have positive first derivatives when you plug in values to the right of square root of 4/3. And the same thing would happen with like -2. So you'd have positive first derivatives over here as well. Right, this is an even function. So remember what this says, what this is telling us, right? These signs of the first derivative tell us about the original graph, right? The graph of the original f. So from negative infinity, up to this negative square root of 4/3, the graph of f will be increasing as you got positive first derivatives. And then between negative square root of 4/3 and positive square root of 4/3, value, the graph of f, the graph of the original, will be decreasing, will be going down because, again, the value of the first derivative is negative. And then from the square root of 4/3 onward, the graph of f will be increasing, will be going up. So you can see from my picture here, from the number line, that this x value at negative square root of 4/3 the graph of f is going to have a local maximum because you're going up and then down. You're at the top of a hill. And we'll go to Desmos and see this, okay? But f has a local maximum at this negative square root of 4/3 value. And then at positive square root of 4/3, see it's decreasing to the left and then it'll be increasing to the right. So you'll be at the bottom of a valley where there's a local minimum. So f has a local minimum, local min at this positive square root of 4/3 value. Now let's actually look just to verify. So back at Desmos here. So here was the function we were given. So again, I'll write it as we had it. Negative 6x divided by, and then 6x squared plus 8. Right, if you look, right, domain's all real numbers, right? There's no asymptotes or whatever. So there's your peak. There's your local max of 0.43. And you see it happens here at negative 1.1547. There's where your local minimum is at positive 1.1457. 1547, that's the square root of 4/3. Right, here's the square root of 4/3, right? 1.1547. So again, look at the picture. They point out a nice thing about Desmos is they highlight where these local max and local min points will occur. They also highlight intercepts, right? 0, 0 is not important here. But they highlight where the local maximums occur and local minima occur as well. And that's at this positive square root of 4/3 and negative square root of 4/3. And those are what I'll enter. And it did say enter an exact answer, right? Don't round anything. So the local maximum value of that function occurs at the positive square root of 4/3. So making sure the 4/3 is all inside the root. And the local minimum value, that bottom of a valley maximum occurred at negative square root of 4/3. And the minimum occurred at positive square root of 4/3. Great. And you can see you saw that in the graph as well. Wonderful. All right, so now this one involves transcendental functions, right? Algebraic functions, you have your input variable, usually x, and all that happens is you're adding, subtracting, multiplying, dividing, and raising to rational powers, roots. That's an algebraic function. Anything outside that is typically considered, it's called a transcendental function. So your exponentials, logs, trigs, inverse trigs, hyperbolic functions. So you see how this one involves an exponential. So we're asked to use the first derivative test once more, to find the location of all local extrema in a particular interval, though. All right, so don't find all of them, just the ones that occur between negative 23/4 and negative 11/4 for this function given below. And if there's more than one, separated by commas, enter exact answers. So this is very similar to the ones earlier with the algebraic functions, right? Where you're entering the x values where the local max will occur, where the local mins will occur. And if none of them happen, right, if it doesn't happen, you enter that empty set symbol. All right. So I'll go into some paper here. Let's write this function out and do the same stuff as earlier. So the function given, and we'll take a look at this in Desmos as well. It's a rational function. You got 4 times, e to the negative 2x. But this, again, this exponential function is what makes this transcendental, not algebraic. Divided by, and then 2x plus 5. All right, so again, I'll state the domain here. The domain of this function. Now, you can plug in anything you want to exponentials. The problem is down here, right? 2x plus 5, that'll be 0 when x is negative 5 halves. So I'll just put this of x, except for put it in that set builder notation. Negative 5 halves or negative 2.5. So everything but negative 2.5 is in the domain here. Okay, so trying to find these critical values, right, where the local max and mins could possibly occur. Find the first derivative. So once again, I've got a quotient rule problem here. So denominator 2x plus 5 times, now the derivative of the numerator I'll be using the chain rule for, right? So this would be itself times negative 2, so negative 8 times e to the negative 2x, and then minus, and then, so denominator derivative of the numerator minus the numerator, 4 times e to the negative 2x, then times the derivative of the denominator, which is just 2. All that divided by the denominator squared. And if you notice, this second term here is also 8 e to the negative 2x. So I could factor that out, 8 e to the negative 2x from both of these, right? Both of them have 8. And in fact, I could pull out negative 8. They both have negative 8 e to the negative 2x. So I'm going to factor that out. And if I do that, I need to have 2x plus 5 plus 1. So I'd have 2x plus 6 as the other factor. Right, there'd be 2x plus 5 still left over from this first term. And then if I pull out, that's pulling out this entire second term, so you still have plus 1 left over. So again, 2x plus 5 plus 1, 2x plus 6. And divided by 2x plus 5, squared. All right, so that should make it easy, to determine the critical values. Now, one of them I'm not even going to worry about. F prime does not exist at x equals negative 5 halves. But that wasn't even in the domain of the original function. Right? I'll still mark it down. Now, this also, let's see, negative 5 halves would be negative 10 fourths. So this isn't even in the interval. Because remember, we're asked to look on the interval from negative 23 fourths to negative 11 fourths in this problem. And this is, negative 10 fourths. So that's not even in there. So again, we don't even have to worry about it. All right. So I'm not worried about that. Now the derivative will be 0 when the numerator is 0 here, and that'll be at negative 3. All right, the 2x plus 6 factor gives that away. This exponential will never be 0, but the 2x plus 6, that'll be 0 when x equals negative 3. And this, right, this is negative 12 fourths. That is in this interval. So there's only one critical value in this interval. All right, now I'll still do this same number line deal. X and f prime of x. You got negative 3 where the derivative is 0. And again, I know this isn't in the interval, but I'm still going to mark it down. This negative 5 halves, negative 2.5 where it's undefined. All right, and then if I were to plug in something between negative 3, so say we plug in something to the left of negative 3 to our derivative function. Now, this exponential factor up here is always negative. This squared factor down here will always be positive, unless x is negative 5 halves, but it's undefined there, right? So really what matters here is going to be the 2x plus 6. So if I plugged in, say, negative 4, this would be a negative number. Then you'd have a negative times negative, positive over positive. You have positive first derivatives to the left of -3. And then if I plugged in, again, this is -2.5. So if I plugged in, say, -2.6, something between, -2.5 and -3, this would be a positive number times a negative. So a negative numerator, positive denominator, you'd have negative first derivatives in between those. And then to the right of that, positive again. Sorry, negative. Negative again. If I plug in something to the right of -5 halves, like 0, and negative, then positive over positive, so negative overall. But again, that's not going to matter, right? We're only focusing on the values between -23 fourths and -11 fourths. But you see from this, then the graph of f will be increasing to the left of -3. The graph of f will be decreasing to the, between -3 and -5 halves, and the graph of f will be decreasing again to the right of -5 halves. And we'll see that in a picture. I'll pull up Desmos. But you see at x equals -3, the graph of f will have a local maximum. Right? It's increasing to the left and decreasing to the right. So it has a local max at -3, and there are no places with a local min. So the graph will have no local minimum value. There'll be no dip, no valley. Right, and let's take a look. So again, here's the function we were given. 4 times e to the -2x power divided by 2x plus 5. Now again, you see I'll put in. Yeah, it's not really nice looking. See, f of -3. Yeah, see that's pretty. That's why you're not seeing it, because the value of f at -3 is -1,613. So like you're not seeing, yeah, you don't see anything to way down here. And you see, I'll zoom in right there. You'll eventually see the top of some hill, right? There should be a local maximum there. It's very thin, very narrow, but you're seeing it hopefully. Coming to view, right? There it is, -3, this -1,613.715, that would be the local maximum value here at x equals -3. And it's, increasing to the left, decreasing to the right. And then you see to the right of -2.5, decreasing the rest of the way, right? This curve up here is definitely to the right of -2.5, is decreasing the rest of the way. You'd have a vertical asymptote at -2.5. Yeah, so only the one local maximum, right? A local maximum occurs at x equals -3, and there is no local minimum, right? So remember, you got to go to find that empty set symbol into the sets area. Great. So back to given the graph. All right, so like earlier, we're given the graph of f prime here and asked how many local maximum values would be on the graph of f. So remember, local max is where the derivative goes from positive on the left to negative on the right. That does not happen in this graph. Right? This is the graph of f prime. You see there's 2 points where the graph touches the x-axis, 2 points where the derivative is 0. At -6 over here, see it goes from negative to positive around that. So you'd have a local minimum. The graph of f would have a local minimum at -6. And then here it looks like 3. It's positive on the left and positive on the right. So it doesn't change sign. Again, for a local maximum to occur at a critical value, it's got to be positive derivative on the left, negative derivative on the right, increasing then decreasing. So this tells me the graph of f has no local maximum values. So I click this black dot over here to 0, and then I don't have any other points to move, and that's it. All right, so back to the same as earlier with the transcendental. See, now we got a logarithmic function here, and something that's not algebraic. And doing the same thing, but only notice, right? Only over the interval from 1 to 3. Right, find all the local extreme values just in the interval between x equals 1 and x equals 3. So the function we're given, we got -3 times x plus, and then 4 times the natural log of 3x. So like I've been doing with all these, right, the domain of this function, right, where this is defined, is only for values of x greater than 0. Right, because remember the log of 0 is undefined, logs of negative numbers are imaginary, so I can only plug in positive numbers here. Now we're specifically told to find the local extremes over this interval here, right? So later on, when I make my number line and stuff, we're going to go back to focusing on the interval from 1 to 3. All right, so first derivative. Just -3. And then remember, natural log of 3x would be 1 over 3x, but then times 3 again, which would just be 1 over x. So plus 4 over x. And so my critical values. Now this is undefined. This derivative expression does not exist at x equals 0. But remember, 0 isn't even in the domain here. So I'm not even really worried about that. Now it will be equal to 0. If you were to put these together, this would be -3x plus 4 all over x, right? If you got a common denominator. The numerator is going to be 0 when x is 4/3. Right? So there's a good critical value, right? 4/3 is actually in the domain. Now I'm going to have my number line here start at 0, even though, because I'm only plugging in positive numbers to this function. So again, values of x, values of f prime. Now at 0, it's undefined, right? I'll mark that down still, but it's not going to matter too much. It's not even, again, it's not even in the domain of the original function. And then here's positive 4/3, right? At 4/3, the value of the derivative is 0. And then if you were to plug in, say, 1, right, something to the left of 4/3 here, into the derivative, you'd have -3 plus 4, which would be positive. So you got positive derivatives between 0 and 4/3. And then plug in, 2, 3, 4, plug in something larger like 2, again, 2, you'd have -3 plus 2, which would be negative. You have negative derivatives beyond 4/3. So the graph of the original function, so the graph of f is increasing up until when x is 4/3, and then the graph is decreasing, right? Got negative derivatives, so the graph of f is decreasing, going down, to the right of 4/3. So 4/3 is where there's going to be a local maximum value, right? It's increasing and then decreasing. So the graph of f, the original function, has a local maximum value here at x equals 4/3, and 4/3 is between 1 and 3, so that's my answer. And notice no local minimum values. And let's see that in a graph. Never hurts to double check yourself, right? So here is the function we were given. It was -3x plus 4 times the natural log of 3x. Notice again, there's no graph to the left of 0 here, right? The domain is only positive numbers, and they see there it is. 1.3 repeating, that's 4/3. So this function has a local maximum value of 1.541, 1.54518 something at x equals 4/3. And notice no valleys, right? It increases to the left of 4/3 and then decreases the rest of the way as we saw in our number line. So local maximum occurs at x equals 4/3 and no local minimum. So again, I have to go to the keyboard here, find the set, that empty set symbol. Great. All right, so this is another one where we're understanding the relationship between the graph of a function and the sign of its first derivative. So graph of f is given below. On what intervals is the value of f prime positive? And give your answer in interval notation. So remember remember f prime is going to be positive wherever the function's increasing, going up from left to right. So that'll be from negative infinity. This is going down for, if I go from left to right, the down arrow, the function's increasing up until when x is -4. So from negative infinity, find the infinity symbol, up to -4. All right, then you got I don't know if you separate them with commas. I'll do the union symbol. They said put in interval notation. So go to sets here, union symbol. Because there's other places, there are other intervals where the function's increasing. Then from x equals -4 to x equals -2, see the graph is going down. The derivative would be negative there. Then it looks like from x equals -2 to x equals 1, the function's increasing. So the interval from -2 to 1 will be the next one I put. And then one more, right? There looks like there's one more place from 3 to infinity, right? From x equals 3 onward, graphs going up. So union symbol again in the sets area. And then from 3 to infinity, right? From x equals 3 onward, the function's increasing, therefore has a positive first derivative. Great. All right, so another one where we're given the graph of f prime, asked how many local maximum values would be on the graph of f, how many tops of hills. So once again, you're looking where the derivative is 0, and if it's going from positive on the left to negative on the right, that's where you're going to have local maximum values on the original graph. So I'll just move these points out of the way real quick. So you see there's that one point at x equals 0, where it's positive on the left, negative on the right. So there's going to be a local maximum on f at x equals 0. And then here at 3, you got negative derivative on the left, positive derivative on the right. So at 3, there's going to be a local minimum. And then over here at 6, got a positive derivative on the left, negative derivative on the right. So there's another local maximum. So there are two values at 0 and at 6 where the original graph will have a local maximum. So I move this to 2, and then one of these points to the 6, where the derivative 0, and then the other critical value of 0 here. At these 2 points, at these two x values, the original function will have a local maximum value. And this is Yeah, just look at the graph and say where the local maximum occurs. Now, I think this is the graph of f prime, right? So once again, they're giving us the graph of the derivative, right? This is not the graph of f. This is the graph of f prime. At what values of x does f have a local maximum? So just like in the previous question, you look at where is the derivative 0? Well, it's 0 at -4, and at 5, and at 7. And then where the original function f will have a local maximum value is where the derivative goes from being positive on the left to negative on the right, increasing to decreasing, top of a hill. So that happens here at -4. See, the value of the derivative is positive on the left, negative on the right. So the original function will have a local maximum at -4. At 5, goes from negative to positive, so you'll have a local minimum at 5. So that's not an answer. But then at 7, positive on the left, negative on the right. At 7, the graph of the original function will have a local maximum. You'll be at the top of a hill. So -4 and 7, and it says separate them by commas if there's multiples. So there are two values, right? The local maxima of f will occur at x equals -4, comma, but also at x equals 7. All right, so that's one of the 4 objectives I'm going to be doing. Again, I'm only doing the ones with the first derivative test for this video. So once again, the graph of f prime is given. So this is the graph of the derivative, not the original. On what interval or intervals is the value of f, the original, decreasing? Interval notation, right? So remember, the graph of the original function will be going down, will be decreasing wherever the derivative has a negative value. So that happens in 2 intervals here. So here's the graph of the derivative. Right, you see it has negative outputs, negative values from -infinity up to -5. Right? So I'll put that interval in. Right? So I got -infinity up to x equals -5. But then there's another one, right? There is another interval where the value of the derivative of f prime here is negative. See, between -5 and -1, positive derivatives, positive outputs. But then from -1 onward, right, from -1 to infinity, the value of this derivative function is negative. So the original function, the original f, would be decreasing. So union, gotta find that union in the sets area. And then from -1 onward, so from -1 to positive infinity, there are the 2 intervals over which f would be decreasing, right? Because again, the value of f prime is negative in those intervals. And they give you kind of like a what f might look like there. All right, so now the graph of f is given below. On what interval or intervals would the value of f prime be negative? So again, this is the graph of f now, the original function. So wherever this is decreasing, the derivative will be negative, right? So f prime will be negative wherever this is going down. So if you look at this, that's from from -infinity up until -4, the function's decreasing, so the derivative will be negative. And then from -4 to 0, got increasing, going up, so the f prime will be positive, so not that interval. And then it looks like from 0 onward, it's going down, so the derivative will be negative. So this derivative, f prime, will be negative from -infinity to -4. So again, interval notation. So -infinity, comma, up to -4. And then the union symbol in the sets area. And then it looks like again from 0 onward, right, from 0 to infinity, the function is decreasing, so f prime would be negative, right? So union, the interval from 0 to infinity, and that should be good. Great. All right, so that's 2 of the 4 that I'm doing today. All right, so this is back with the algebraic functions. Okay. So fine, just like the others with the algebraic and the transcendental functions, right? You're given a function, asked to determine where, at what x values will these local maximums and local minimums occur. All right, so this is a polynomial function, right? Just a product. I'm going to be using the product rule when I do the derivative here. Now, I mean, you could multiply the whole thing out. It would just be probably a little annoying to multiply that all out. So here we have 2x minus 2 cubed multiplied by, and then 3x minus 1 squared. Now the domain of this function is all real numbers, right? It is a polynomial function. So whatever critical, now the derivative will be a polynomial as well, right? So I don't have to worry about being undefined. So we're just going to really focus on, where the derivative is 0. All right, so the derivative, going product rule here, so I'll call this the first factor and this the second factor. So remember, leave one of them alone. So 2x minus 2 cubed multiplied by the derivative of the second one. So that'd be chain rule because I'd have 2 times this to the first, but then times 3. So that'd be 6 times 3x minus 1 to the first. And then plus, and then the other way around where I do the derivative of the first. So in chain rule, it'd be 3 times this squared, then times the derivative of this. So 3 times 2, so 6 here, times the 2x minus 2 to the second, and then leave the second factor the way it is, 3x minus 1 squared. All right, and then I'm going to factor some stuff here, right? Notice that both of these, they have a factor of 6 in common. They have 2x minus 2 squared in common. And they both have 3x minus 1 to the first in common. All right, and if I remove those, all right, so I take out 3x minus 1 to the first, take out 2x minus 2 squared, take out the 6. What's left over? You'd have a 2x minus 2 here, plus, and then a 3x minus 1 here. And if you add those up, that'd be 5x minus 3. So that'd be the other factor. All right, there'd be a 2, again, there'd be a 2x minus 2 left over here, plus there'd be a 3x minus 1 left over here. Add those up, 5x minus 3 for the other factor. So now it's in a nice factored form where you can easily see what the critical values are going to be, right, without multiplying it all out. Now it's never going to be undefined, it's still a polynomial, but it will be 0 at multiple places. So the derivative, this will be equal to 0 at, x equals 1 for this first factor, x equals a third for this next factor, the 3x minus 1, and x equals 3/5. And if I make a number line for this, being a polynomial, you should know a lot more about polynomials from like pre-calc. Make a number line for this derivative. Mark down these critical values. Now, third is smaller than 3/5. All right, so you'd have a third and 3/5, and those are both smaller than 1. So at each of these values, the derivative is 0. And then look at your derivative here. The derivative would be some fourth degree polynomial, right? That's a degree 2, degree 1, degree 1, fourth degree with a positive lead coefficient. So you'd have to be doing this. You'd have a positive output to the left of 1/3 here, The multiplicity of 1/3 is odd, so it would cross over. You'd have a negative derivative between 1/3 and 3/5. The multiplicity of 3/5 is also odd, so it would cross over again, and you'd have a positive derivative between 3/5 and 1. And then the multiplicity of 1 is even, right? This is two of those factors. So it would bounce off the axis, and stay positive to the right of that. So again, you can plug in values if you wish, but knowing what we know about polynomials, or hopefully what you know about polynomials, you should be able to do that pretty quickly with the polynomial expression. So again, the graph of f will be increasing on this interval. F will be decreasing on this interval between 1/3 and 3/5, and then increasing pretty much the rest of the way. So there's only one local max, right? F has local max at x equals 1/3. So you're going from increasing to decreasing there. F, the graph of the original function, has a local minimum value at x equals 3/5, right? Because you're going from decreasing to increasing, and then neither of those things at x equals 1, because it's going from increasing to increasing again, right? So my two answers are 1/3 and 3/5. 1/3 for the local max location and 3/5 for the local min location. And you can go to Desmos and doubly verify that, but I'm not this time. And so local max will occur at 1/3, and the local minimum will occur at 3/5. Great. Again, they point out that 1 is not a good one. All right, so this one, they're giving us a table. All right, so they tell us the critical values, -2, +2, +3, and a table showing me the values of the derivatives in intervals around these critical values, right? So to the left of -2, negative first derivative, f would be decreasing. Between -2 and +2, negative first derivative, so f is decreasing again. Still more. From 2 to 3, positive first derivative, so f is increasing. And from 3 onward, negative first derivative, so f is decreasing. So they're saying at what value or values of x do any local maxima occur? So remember, that means I'm going from positive derivative to negative derivative, increasing to decreasing. Well, there's only one interval, one place where it goes from increasing to decreasing. That would be at x equals 3. So to the left of 3, increasing, and then to the right of 3, decreasing. And that's the only one. So x equals 3 is the only place where f has a local maximum. Right. And then we have the one more objective here today on first derivative tests with those transcendental functions. So again, they give us a specific interval to look over, so just the interval from 0 to 2 pi here. Because there's all sorts of, when you're looking at cosine, remember cosine and sine are waves. They're constantly going up and down as you go from left to right. So loads of local max and mins. We're only asked to find the ones, between 0 and 2 pi. All right, so the function we're given is cosine of 3x and -2. Now the domain is all real numbers, right? The domain of this function is all real numbers. You can plug anything you want into the cosine function. But we're asked to look specifically on the interval from just 0 to 2 pi though, all right? So I'm going to keep that in mind. All right, so first derivative, remember the derivative of the cosine of something is negative sine of that thing, but then, chain rule, if you multiply them by 3, so you have, negative times the derivative of 3x. And then the derivative of -2 is 0. So -3 times the sine of 3x. Now, being the sine function, this will never be undefined. So you're only looking for the critical points, critical values. And when is this equal to 0, right? So negative 3 sine 3x will be equal to 0 when the sine of 3x is equal to 0. And that'll happen when 3x is any multiple of pi, so k times pi, right, where k is some integer. So x has got to be multiples of pi over 3, and then we're just going to take all the multiples of pi over 3 that are between 0 and 2 pi. So on the interval from 0 to 2 pi, x is going to be 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, and 5 pi over 3. Because then 6 pi over 3 would be 2 pi, and then you're too big, right? So there are 5, possible critical values here. And if you were to look at the graph of this derivative function, and I'm just going 0 to 2 pi, all right? I'll mark these down. You got pi over 3, 2 pi over 3, 3 pi over 3, which is pi, 4 pi over 3, 5 pi over 3, right? So again, these are values of x, and we're looking at the derivative, right? This is a number line for f prime. So remember how sine is all wavy and stuff, right? Sine of 0 is 0. So again, the value of the derivative is 0 at all these places, even at the ends. Now, if you took something smaller than pi over 3, then, I'll put in like pi over 6. Because if x is pi over 6, that'd be sine of pi over 2, which is 1. So negative, so you have negative derivatives here, and then it's going to fluctuate, right? Because again, sine is all wavy. So negative derivatives here, positive derivatives, negative derivatives, positive derivatives, negative derivatives, positive derivatives. So you got f going down, f going up, going down, right? This happens with your cosine function, right? The original function was this cosine thing. It's going to keep going up, down, up, down, up. So there are multiples of each. So see here at pi over 3, local min, right? Decreasing and increasing. At 2 pi over 3, local max, right? It goes increasing and decreasing. At pi, local min. At 4 pi over 3, local max. And at 5 pi over 3, local min. Again, because of the whole fluctuating wavy nature, that's going to be happening. So I got a couple maxes, 2 maxes and 2 maximum locations and 3 minimum locations. So I got to separate those with commas. So yeah, there's 2 locations between 0 and 2 pi where there's going to be a local max. So 2 pi over 3. I'll pull up the basic keyboard so the pi symbol's there, right? So 2 pi over 3 and 4 pi over 3 are locations where you have a local max. And there are 3 locations between 0 and 2 pi where the function will have a local minimum. And that was at pi over 3, pi, and 5 pi over 3. Yeah, don't want to type pi, the pi symbol there. Pi over 3, comma, pi, comma, 5 pi over 3. And that should be good. Again, you can look at the graph in Desmos or something if you want. All right, then once again, pretty similar, another cosine wave, right? So there should be a pretty good fluctuation here. Now, because it's not cosine of 3x, the period's only 2 pi, right? The cosine of 3x earlier, the period was 2 pi over 3, so it repeated more often, it repeated with a higher frequency, smaller period, higher frequency. So probably shouldn't see as many here, but still pretty similar. Let's do another page. Pretty similar to the last problem. So the function we're given, 2 minus 2 cosine x but we're only looking on the interval from 0 to 2 pi, even though the domain is all real numbers, but not including 0, not including 2 pi. So the derivative would just be positive 2 sine x, and my critical points are wherever the sine is 0, so that would be a pi, right? Because it's 0 at 0, and then pi, and then 2 pi, but 0 and 2 pi aren't included here. So I'm going to my number, 0 to 2 pi only. Look at the derivative at pi at 0. And it's also 0 at these values, but again, we're not including them. And then between 0 and pi, say I plugged in pi over 2, you'd get a positive derivative, 2 times the sine of pi over 2, and then negative derivative after that. So f going up, f going down. So there's only the one value where there's a local max. There'd be a local maximum at pi, and no local minimums in this interval. Now there would be a local minimum at 0 and at 2 pi. It would keep alternating, but they only ask for the ones in between. There's only one local max, and that occurs at x equals pi, and no local min. So that empty set symbol in the sets area. Great. All right, so that's going to do it for this video. I said I would be going through the objectives here in the first derivative test heading. So this will be part 1. Another video coming out after this I'll make is going to be, I'll start up here in concavity and points of inflection will be part 2, and then the second derivative test will be part 3. All right, so hopefully watching this helps you get through all the problems that you're going to be working on related to these 4 objectives here, and thank you very much for watching.